All right, guys, chapter 7.3, voltage and sources of potential energy. So in this topic, we're going to be looking at what is voltage in a circuit and what provides the energy that is required for an electric current to flow through a circuit. So we're going to look at electric potential. We're going to look at what is electric potential, and we're going to look at what is electric potential energy. So those are two different terms. And if you're able to calculate and describe what voltage or electric potential is, then you will have been successful in this lesson. So all electrical devices like this very relevant diagram of a CD player um, all need to have some source of electrical energy to allow the device to function. So when we connect up our batteries into our CD player, the charges will move out of the battery pack, go through and do whatever is needed to in that device, and then flow back to the battery pack to pick up more energy. So your battery pack is the source of energy. So in your CD player, it would be being used to spin the CD around, to move the laser, to power the amplifiers, to output the music or the sound signal to your headphones. So all of that energy has to be supplied initially by the chemical energy stored inside your batteries. So what we can, another way we can describe voltage is the electromotive force. So in order for our electrons to flow around our circuit, as we know from Newton's first law, we need to have some unbalanced force that acts on our object to cause it to change its state of motion. So the same thing applies to an electron. An electron's not going to move unless you apply a force to it to make it do so. So another way we can describe voltage is by calling it the electromotive force. So it's the force that causes electrons to move. Now, as much as I hate to admit it, the chemists are onto something here, because what they are doing with electric circuits using batteries is we're converting stored chemical potential energy and converting it into electrical energy to cause our electrons to move through our circuit. So the way this works is in our battery, usually it's an oxidation reduction reaction that causes one terminal to become positively charged and the other terminal to become negatively charged. So because of that difference in potential between the positive and negative terminals, our electrons will experience a force and travel around our circuit. Remembering last time I talked about the difference between electron flow current and conventional current. So our electrons will flow out of the negative terminal, pass through our circuit, and then we'll return back to the positive terminal. So electric potential difference is what we measure in voltage. So the difference in the potential between the negative and the positive terminal is how we describe the voltage of our battery. The SI unit for voltage is the volt, where 1 volt is equal to 1 joule of energy supplied to 1 coulomb of electrons. So 1 volt equals 1 joule per coulomb. Some typical electromotive force EMFs or voltages of some common batteries. So the battery in your car generally puts out 12 volts. Any of the batteries that you'd use around home, AA's, AAA's, C's, D's, they put out 1.5 volts. 9-volt battery very conveniently puts out 9 volts. A lantern battery, they're those big sort of um, like rectangular prism type batteries that used to be used in big like dolphin torches. They're not so common anymore. Please excuse Mr. Stanley's 90s reference there. EMF, unbelievable. You can look up that song if you want to. That's not the EMF that we're talking about here. So let's have a bit of a think about potential difference and compare it to the difference in gravitational potential energy. So if you look at the top diagram, we have a little man of mass m. He's walking up a set of stairs through some height delta h, and he's requiring some work to enable him to do that against the acceleration due to gravity. So we have the mass m, we have the gravitational field g, we have the delta, the change in height delta h. So we can apply the same analogy to our little electron that is moving up through this change in voltage in the bottom diagram. So we initially start off with our little electron having no electric potential energy, but by moving it against some electric field, we can increase its potential energy by doing work on it. So the work done on our little charge Q is equal to the charge times the change in the voltage that we are undergoing. So the voltage can be considered to be, or can be thought of as, the work done on a unit charge or charge of 1 coulomb to move it from one point in an electric field to another. So we can call that or we can think about that as voltage equals work done divided by the charge in coulombs. So V equals W on Q is a formula to determine how much voltage or how much electric potential is required to move an object from one point to another. As I said before, the units are measured in volts with a capital V, and 1 volt is equivalent to 1 joule per coulomb of electric charge. So a volt, we can think about that as the potential difference between 2 points, and it's 1 volt if 1 joule of work is done by moving 1 coulomb of charge from one point in our circuit to another, or from one point in an electric field to another. If we think about our circuit, we can measure the electric potential at a particular point in our circuit. So the particular, like at, say, if we had a circuit with a light bulb in it, the potential difference, or the potential, sorry, at a point within our circuit would be the potential difference between that point in the circuit and the earth. So the earth is considered to have zero potential. The earth can absorb or supply as much electric charge as needed. So if we were to measure the difference between zero potential and the potential at a particular point in our circuit, that would be the potential difference between that point, or the voltage required to move our charge from Earth to that point. So if we sort of equate EMF, or the work done to move our charge through our electric field, we can equate that to the change, or the work done to move our object with mass through a difference in height in our gravitational field, so that we know that gravitational potential energy equals mass times gravity times height, or the work done to move from one point to another in gravity to lift an object through a certain height is mgh. So rather than looking at objects with mass, we're looking at objects with charge. So we're not having m, we've got q. We're not looking at objects in a gravitational field. We're now looking at objects in an electric field. So we don't have G, we have capital E. And just because we don't have, like in gravity only ever acts vertically, so we can only describe it as the change in height, whereas an electric field can act in all directions. So it's just the distance that you move through that field. So in an electric field, the work done on an object or on an object with charge is equal to QED. So the charge multiplied by the electric field strength multiplied by the distance that you moved it. We'll get more into that when we're doing Unit 3 later on next year. So for now, you guys just need to know the formula V equals W on Q. So the voltage or potential difference between 2 points equals the work done divided by the charge in coulombs. So just the difference between electric potential and electric potential energy. So electric potential is measured in terms of volts and has the symbol V. It's not an energy. So if we think about electric potential energy, its symbol is W because it's the work done to move an object, and it's measured in joules. So don't get confused between electric potential and electric potential energy. If we look at page 217 in the book, the definitions that Richard gives are: electric potential is the amount of work needed to move a unit or 1 coulomb of charge from one point to another, or the electric potential energy per unit of charge that an object contains. whereas electric potential energy is the actual energy stored in a charge, or the capacity of the charge carrier to do work due to their position in an electric circuit. So just like gravitational potential energy is the potential for an object to do work due to its position in a gravitational field, if you lift a rock up and then drop it, it will do work as it falls back to the ground. So the same thing happens with an electron moving through our circuit. Due to its position in the circuit, it will have some energy that it's able to then do work with. So that's the whole point of electric circuits, is to allow objects to convert electrical energy into useful work. So the potential difference, we can measure the potential difference between 2 points in a circuit. So if we know the voltage at point A and we know the voltage at point B, as our charge Q moves between points A and B, it will pass through a potential difference, or some delta V between those 2 points. Usually though, in an electric circuit, we assume that one of our terminals of our battery is at zero potential, or has 0 volts of potential. So as our electrons move through the circuit, they start off, let's say this was a 9-volt battery, it would have 9 volts of electric potential when it leaves the negative terminal, and as it returns to the positive terminal, it will have 0 volts of potential. Now, it can be a little bit counterintuitive when we talk about combining cells. So when I talked last lesson about the symbol for like a battery in a circuit being one long line and one short line, that's actually a 1.5 volt cell. So you can think about like the long line represents 1 volt and the short line represents half a volt. So if I put 4 1.5 volt cells next to each other in series, then as our electrons move from the positive terminal of that battery and then they pass through our battery, they use that converted chemical potential energy to be transferred into electrical energy. They go from 0 volts of potential when they enter the positive terminal. They pick up 1.5 volts through the first cell, 1.5 volts through the second cell, 1.5 volts through the third cell, 1.5 through the fourth cell. So they've picked up 6 volts in total. So when we add batteries in series, we add the EMF of those batteries. However, when we add batteries in parallel, an electron, if you consider a single electron, when a single electron gets to this junction of the 3 positive terminals, that single electron can't flow through all 3 cells at the same time. So our electron will choose to either go through the top cell, through the middle cell, or through the bottom cell. And you can see then that will only ever pick up 1.5 volts of EMF. So the potential difference between the positive terminal on the left and the negative terminal on the right is only ever 1.5 volts, regardless of how many of those cells you add in parallel. What we do change by adding cells in parallel is we allow more electrons to flow through than could flow through in our series cells. So we actually get 3 times the current flowing out of our cells in parallel. So when you have cells in series, you add the voltages. When you have cells in parallel, then your currents will add. So when we have a resistive element in our circuit, actually, no, this isn't a resistive element. This is looking at coming back. Yeah, so when we have a circuit, we must have a source of EMF and we must have a resistive element that uses up our electrical energy. So if we trace the path of an electron as it goes through our circuit from A to B to C, we see that the electron's coming into our battery with no electric potential. So it has 0 volts left as it's passing back into the battery. As it passes through the battery, those filthy chemists do their magic and they give our electrons some of the stored chemical potential energy from the battery, and that turns into electric potential energy. Those electrons then pass back out of the battery with 6 volts of electric potential. So we have potential rise as we go through the battery. The electrons then will, we can consider the wires to have no energy usage. So our electrons will contain that 6 volts of potential until they get to our load or our resistive element. and then as they pass through the load, they will give up their electrical energy, converting it into light or heat or sound or whatever the resistive element is, like whatever the useful work is that that element is doing. Once they've given up that energy, they then just flow back through the circuit, back to the battery to pick up that electric potential energy again, and then they can pass around and around the circuit, continually gaining energy as they pass through the battery and then losing energy as they pass through our load. So we measure voltage with a voltmeter. So last time we talked about measuring current with an ammeter, and I said that ammeters have to be connected in series because the ammeter will actually count the amount of charge that is flowing through it. However, our voltmeter has to be connected in parallel with our load or with our resistive element. So here we're trying to measure the voltage used by this light bulb. And to do that, we have to connect our voltmeter, which has the symbol of a capital V inside a circle. We have to have that connected in parallel across our light bulb rather than being connected in series with it. So why do you think that might be? What do you think, what are we doing if we're measuring the voltage that is dropped across our light bulb? So we'd be measuring the voltage of the electrons as they pass into one side of the light bulb, and then we'd be measuring the energy of the electrons as they come out the other side of the light bulb, and we'd be measuring the potential difference between those two sides of that light bulb. So that's why we have to always connect voltmeters in parallel with the element that we're trying to measure the voltage drop across, because we're actually measuring the potential as our electrons go into one side and then measuring the potential as they leave the other side, and your voltmeter will display the potential difference or the voltage drop across that element. So there's a few links there that you can go to if you would like to do some extra reading about this, but as always, there is work in Education Perfect and CK12. The last slide shows you that. But just as a couple of review questions here, we have two devices, X and Y, that are measuring some property of our electric circuit. Which of the following descriptions is correct? I'll give you a second to read through those. So which one measures current, which one measures voltage, or do they both measure voltage, or do they both measure current? So hopefully everybody chose option 1, that because it's connected in series, X must be an ammeter measuring the current. Because it's Y is connected in parallel, it must be a voltmeter measuring voltage. And how does the current entering our resistor compare to the current leaving the resistor? Who remembers last lesson? What did I say about current flowing through a series circuit? Remember, current is just the measure of the number of electrons that are flowing through the circuit. So you consider that to be like a pipe with water flowing through it, consuming there's no leaks in the pipe. The amount of water flowing out of the pump and then passing through our load will be the same as the amount of water passing back into the pump at the other end. So because our electrons are physically bound inside our wires, we can't lose any electrons as the current flows around the circuit. So therefore I1, the current going into the resistor, must be the same as I2, the current leaving the resistor, because the number of the electrons or the amount of charge per second flowing through that series circuit must be the same at all points. So option 3, I1 is equal to I2. So you can now go and have a look at Check Your Learning 7.3. There is work assigned to you on Education Perfect and CK12. We're now done those first 3 key formulas. We've looked at voltage equals work divided by charge. So next lesson to finish off the week will be on electric power. Thanks very much.